The paper presents a novel method for storing quantum information in a generalized Dicke model, which consists of a system of three-level atoms interacting dipolarly with a single mode of an electromagnetic field. This system has three different atomic configurations, namely Xi, Lambda, and V. The authors focus on the mathematical structure of the model, representing the matter contribution by a U(3) group structure and constructing a natural SU(2) subalgebra for each atomic configuration using linear combinations of the matter operators. In particular, they identified two SU(2) local rotations that decouple the M-dipolar interaction between two of the atomic levels, leading to an effective Hamiltonian consisting of a two-level Dicke model plus an isolated atomic level, and a remnant term corresponding to a one-body matter interaction between the atomic levels with a forbidden dipolar transition. For the Lambda and V configurations, the one-body matter interaction disappears when two of the atomic energy levels are degenerate, equal detuning, resulting in the expectation value of the population of one or the other atomic level becoming a constant of motion that vanishes for the ground state. The authors also use the fidelity and the susceptibility of the fidelity between neighboring states to determine the quantum phase diagram for a finite quantum system with a fixed number of atoms. These quantities detect any abrupt change in the state of a system when a control parameter is varied. They find that the phase diagram remains invariant under the local SU(2) rotations, as the minima of the fidelity remain at the same loci as those for the original Hamiltonian. The paper is structured as follows. Section 2 establishes the generalized Dicke model. Section 3 presents the SU(2) structure which arises naturally in each configuration and shows the particular rotation that decouples a level in every case, and Section IV gives the expectation values of the atomic energy levels, as well as the quantum phase diagram. The paper discusses a generalized Dicke model for a system of Na atoms with three levels interacting dipolarly with a single mode of electromagnetic field. The Hamiltonian of this system is given in equation 1, where the matter operators obey in SU(3) algebra as defined by equation 2. The nature of the matter-field dipolar interaction requires that at least one of the coupling constants μJk be null, which gives rise to three atomic configurations: Xi, V, and Lambda. Each configuration has its own parity operator and corresponding Hamiltonian, which preserve the parity of the number of excitations. In order to eliminate the interaction between one pair of atomic levels with the EM field in the cavity, rotations through the third element in each corresponding SU(2) subalgebra are applied, as shown in Table 1. These rotations, given by equation 4, involve selecting the parameter alpha such that certain interactions vanish in the transformed Hamiltonian, H. Depending on the configuration, different values of alpha are chosen to eliminate specific interactions, as detailed in the text. The transformed Hamiltonian, H, is expressed in equation 6, where the transformed frequencies and coupling constants are denoted with a tilde. This new Hamiltonian can be used to store quantum information effectively in the generalized Dicke model via a simple rotation. The paper explores the effects of these rotations on the system, providing new Hamiltonians that can be used for various applications. The research proposes a novel method for storing quantum information in a generalized Dicke model using a simple rotation. This approach eliminates the coupling of the M field with a pair of atomic levels, introducing a new matter one-body coupling between atomic levels without a dipolar transition. The intensity of this one-body matter interaction vanishes in certain configurations, reducing the three-level Dicke model to an effective two-level Dicke model plus an isolated atomic level. The process is demonstrated in the Lambda configuration, where rotations isolate specific atomic levels, enabling the exchange of information between qubits. The fidelity between the qubits is exactly 1, ensuring that information stored in one qubit can be retrieved by the other. This method can also be applied to the V configuration, but not in the Xi configuration due to its population characteristics. The Hamiltonian is reduced to an effective Raman transition of a two-level Dicke model plus an isolated atomic level, with eigenstates obtained through numerical diagonalization. This innovation offers a promising procedure for storing and retrieving quantum information. The research discusses storing quantum information in a generalized Dicke model via simple rotations. Starting from an eigenstate of H lambda, a rotation U12, arctan, micro 13, micro 23, is used to store information, followed by a retrieval rotation U12, minus arctan, micro 23, micro 13. This process involves quantum Rabi oscillations in qubits formed by levels omega 2 and omega 3, with the stored information retrieved by switching to Rabi oscillations in the qubit omega 1 and omega 3. Numerical results show the robustness of this method, even with non-degenerate atomic levels. The expectation value of the population for each atomic level under special rotations is calculated, demonstrating that the population of the isolated level is negligible in the Lambda and V configurations when levels are equally detuned. The fidelity between stored and retrieved states approaches 1 as the levels approach resonance. The one-body-matter interaction term vanishes in degenerate conditions but has an effect on the isolated atomic level when not degenerate. The Hamiltonian of the system is transformed under rotations, showing significant changes in atomic populations, particularly in the collective region where other atomic levels contribute importantly. The expectation value of the atomic population of the decoupled state remains close to zero, demonstrating the robustness of this property. The research paper explores the concept of storing quantum information in a generalized Dicke model through a simple rotation. The study focuses on 3 atomic configurations, Xi, Lambda, and V. To understand the phase diagram of the system, the fidelity between neighboring states is calculated using equation 11. This fidelity is then used to detect abrupt changes in the ground state of the system as control parameters are varied. In order to determine the phase diagram, the fidelity between neighboring states is calculated along lines that pass through the origin, which allows for the detection of all minima. Figure 4 presents the phase diagram for the Xi configuration, showcasing the minimum of the fidelity between neighboring states in both resonant and non-resonant cases. The results are compared with the separatrix obtained from a variational solution using coherent states as test functions, given by equation 13. The paper also discusses how the phase diagram remains invariant under SU rotations, even when these depend on control parameters. This invariance is demonstrated in Figs. 46, where the stability and equilibrium properties are shown to be the same for the original and rotated Hamiltonians. The expectation values of the atomic populations are depicted in Fig. 3, illustrating the negligible population of uncoupled levels. The calculation of the fidelity between neighboring states along lines maintaining one coupling strength constant does not always detect all minima, but this limitation can be overcome by considering linear and/or quadratic functions that pass through the origin. The paper concludes that the phase diagram is invariant under SU rotations, and the stability and equilibrium properties are the same for the original and rotated Hamiltonians. Storing quantum information in a generalized Dicke model via a simple rotation, pages 11 and 12. The research proposes a methodology for retrieving stored quantum information in atomic systems interacting dipolarly with a one-mode radiation field. It focuses on the generalized Dicke model and the use of a simple rotation applied to the Hamiltonian. The study explores various atomic configurations, including the Xi and V configurations, analyzing their separatrix shapes as a function of the number of atoms and detuning values. Figures 4, 5, and 6 provide detailed illustrations of these separatrix shapes for different atomic configurations and detuning conditions. The results show that as the number of atoms increases, the quantum separatrix tends towards the variational solution, indicating a stable transition from the normal to the collective region. The methodology's robustness is demonstrated through numerical examples, including the atomic V configuration under non-equal detuning, where the population fidelity is less than 1. However, as the system approaches resonance, the fidelity between states approaches 1, suggesting a high degree of accuracy in retrieving stored quantum information. The paper discusses the storage of quantum information in a generalized Dicke model using a simple rotation. It begins by introducing the concept of a rotation operator kjk, which is defined as the difference between two atomic transition operators, AJK and AKJ. This rotation operator is then used to define a unitary transformation UJK, alpha, which transforms the atomic transition operators into their rotated counterparts, ALM, J, K. The authors derive differential equations for these transformed operators and solve them to obtain explicit expressions for the transformed operators in terms of the original ones. These transformations are valid for an n-dimensional algebra and are applied to different atomic configurations, such as the Xi, Lambda, and V configurations, each with its own specific rotation defined by the forbidden atomic transition. The paper also presents a graphical representation of the separatrix for atoms in the lambda configuration, comparing the quantum separatrix with the corresponding variational solution. As the number of atoms increases, the quantum separatrix approaches the variational one. This method allows for the calculation of the full energy spectrum of the system, which can be written in bands associated with the number of particles NL equals 0, 1, Na of the isolated Fock state. The work is supported by the fact that, for an appropriate value of alpha, one may eliminate one term of the matter-field interaction in the three-level Dicke model with a single electromagnetic mode. This has implications for the storage of quantum information in such systems. The paper concludes with an acknowledgement of the support received from DGAPA-UNAM under Project Indiana 100323 and provides an appendix detailing the rotation of the three-level Dicke Hamiltonian with one electromagnetic mode for arbitrary alpha. The research discusses storing quantum information in a generalized Dicke model via a simple rotation. It focuses on various configurations like Xi, Lambda, and V for atoms. The Hamiltonian for each configuration is derived, highlighting the role of parameters alpha and the dipolar transitions. For instance, in the Xi configuration, the Hamiltonian eliminates dipolar transitions by choosing specific values of alpha. The paper also explores the fidelity between neighboring states, introducing an approximation for the overlap between states psi, micro, and psi, micro plus delta micro, under an infinitesimal unitary transformation. This leads to an expression for the squared absolute value of the overlap, which is simplified using the fact that certain terms are real numbers. Numerical results show that the minima of the whole expression and the first term are the same, indicating the significance of the first term in the context of fidelity. The study's findings and methods contribute to the understanding of quantum information storage in various atomic configurations. The research paper discusses the storage of quantum information in a generalized Dicke model through a simple rotation. The Dicke model, first proposed by R.H. Dicke in 1954, is an essential theoretical framework for understanding the interaction between light and matter in quantum physics. The model has been extensively studied in various contexts, including quantum phase transitions and symmetry groups. The authors focus on the concept of a simple rotation as a means to store quantum information within the generalized Dicke model. This approach involves applying a unitary transformation to the Hamiltonian of the system, which results in the invariance of the ground state diagram for certain special rotations. This invariance is crucial for maintaining the integrity of the stored quantum information. The paper also references several previous studies on the Dicke model, including its application to quantum phase transitions and symmetry groups. These references provide context and background information on the theoretical foundations of the research. In addition to the theoretical aspects, the paper includes a list of references that further elucidate the concepts discussed. These references span multiple decades and cover topics such as quantum mechanics, symmetry groups, and quantum phase transitions. Overall, the paper presents a novel approach to storing quantum information using a simple rotation in a generalized Dicke model. By leveraging the invariance of the ground state diagram under specific rotations, the authors propose a new method for preserving quantum information. This research contributes to the ongoing efforts in understanding and developing quantum computing technologies, particularly in the context of the Dicke model.